So it's my moment to introduce Burton from the University of Queensland, who will tell us about the topology of tiny machines.
Yeah, so okay, so thank you. So I'm here as somehow a hardcore software person, and I plan to talk about algorithms that you would never want to implement. And actually I'm lying a little bit when I say that, but essentially the study here is not how fast you can make the code, but how small you can make the code. And when I say how small, I mean how little memory you can use. Right? So in one sense, space complexity is uninteresting, because if you have a machine and you run out of memory, you can always stick in another hard drive and then stick in another hard drive and keep going until the computation finishes. Right? But well, unless you have an Apple device like I do, in which case you have to buy a new machine. But in practice, it is a problem that you occasionally run into. So if you're enumerating normal surfaces, and if you're using Regina prior to about 5 years ago, then it was using what's called the double description method to enumerate vertex normal surfaces in a triangulation. And if you're doing unknown recognitions, connected sum decomposition, you're using this machinery, right? And the double description method, it's like an inductive algorithm that goes through several stages from start to finish, processing each linear equation at a time. And at each stage, it can have an exponential blow up in the amount of intermediate data that it stores. And what you would see in practice is that your machine would run out of memory. And it was not the time that ran out first, it was somehow the space, right? You would leave it running for a couple of hours, and then you would hear the hard drive churning, and you realize it's out of memory and it's on a swap space, and you kill it now because it's not going to finish. So space complexity does matter a little bit, but I'm not talking about exponential space complexity here. I'm talking about tiny, tiny space complexity. So logarithmic space and then constant space. So having said all of that, I promise to write something on the board in a moment. But if you are not interested in theoretical computer science, you should still care about space complexity. And this is something that I appreciate now much more than I did even half a year ago. And I'll come back to this. But essentially the ideas in this talk are an interplay between the following things. So you have space complexity. So this is the measure of how much memory your algorithm is using. Not time, but memory. You have parametrized complexity. So parametrized complexity, this is where you don't just measure the running time in terms of the input size, but you give it a more fine-grained measure. Right? So maybe you measure it in terms of the input size and the Hagar genus of the manifold, or maybe you measure it in terms of the number of crossings in the knot and the diameter of the graph that you get by drawing the knot. Yeah? And then you want to quarantine all the exponential growth into one of the parameters. So you kind of want to identify exactly where the exponential growth is coming from. So there's parametrized complexity, and then over here we have finite state problems. And this is really running things on finite state automata, right? Which is essentially machines with constant memory. And somewhere in the middle of here, I am going to put software, because although this is, for me, this is like a foray into something that is purely theoretical with no implementation coming out the other end. Actually, it's looking less like this than it was. Right? And so I have an honors student whose name I threw up on Wednesday during the software demo, Alex Eastwood. So Alex is writing up some code that will exactly use this sort of machinery to solve problems that you don't have algorithms for. So you say, I would like to test whether this triangulation is a disk, and you don't tell it how to do it. The computer doesn't know, you haven't given it an algorithm, you just give it a description of the problem. So this is the sort of thing that you studied in AI if you did Prolog in the 1980s. Right? But anyway, they are coding that into Regina for their honors thesis. So let me start with finite state machines, because finite state machines are things that maybe, who's seen finite state automata? Okay, excellent. So I'm just going to draw one, and then we talk about it very, very briefly. So finite state automata. I will sometimes call them finite state machines. I will sometimes call them deterministic finite automata. I have a bit of a problem because I learned one thing and then I teach another nowadays at the university. But yeah, they're all words for the same thing. The idea is you have a finite number of states that the machine can be in. So suppose you're given a string of ones and zeros, and you want to measure whether the number of ones is equivalent to 0 mod 3. Right? whether the number of ones is a multiple of 3. Yeah? So you start the machine at some state here. Whenever you read a 1 in the input, you follow the 1 arrow. Whenever you read a 0 in the input, you follow the 0 arrow. And so you just take the input string, start at the start state, and for each piece of input you go bonk, 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 and jump around the machine until your input runs out. Right? And this is a state where you say the answer is yes, and these are states where you say the answer is no. Right? So this will measure whether the number of ones is a multiple of 3. So are there any questions about this? Yeah. Yeah. So the idea is if you're in this state, then the number of ones is equivalent to 0 mod 3. If you're here, it's equivalent to 1 mod 3. Oh, what are the zeros? Because, okay. The zeros, because I'm actually solving a different problem than what I described. I'm testing whether the number of ones is equivalent to the number of zeros mod 3. Let's do this with the zeros. Yep. Okay, excellent. Okay, so there's a bug in my code. So the point of these finite state machines is that you actually use them. Right? You actually use them in software. This is not just a theoretical thing to scare first-year computer scientists. Yeah? So where do you use them? Does anyone know where you use them? grep, right? So grep. So if you sit at the command line and run grep, or if you're hardcore and you use something like Vim or Emacs that lets you search by regular expressions, the point with grep is it's a tool that lets you search for a piece of text in a file, right? So I want to search for the word Lackenby because I want to find all the best theorems, right? So I say grep Lackenby text file and just run through the text file and spit out all the matches. And that's a little bit boring because you just walk through the text file, a little bit of work, and to make it fast enough. But you can do more interesting things. You can say, find me any word that starts with an L followed by one or more vowels followed by a consonant. Yeah? So you can give patterns, and the patterns can be patterns that don't have a fixed length. So you can say things like, if I want to find, if I want to find a sequence where the number of ones is equivalent to 0 mod 3, then what I want is any number of zeros followed by a 1 and any number of zeros, a 1 and any number of zeros, a 1 and any number of zeros, and that whole sequence can happen any number of times. Right? So this is a pattern that you can feed to grep, and grep will search for this kind of pattern in your text file. And these patterns can be very complicated, but grep has a running time which is linear in the size of your text file. And the reason the running time is linear is because what grep does is you give it a regular expression, one of these patterns, it builds a finite state machine to recognize that regular expression, and then it just feeds your text file through the finite state machine. And so the running time is linear because every time you have a letter in your text file, it just jumps to a new state, and that's it. Right? So for free, anything that you can do on a finite state machine is going to be linear time. So this is already an immediate link between space complexity and time complexity. Where I'm going with if I didn't spend the entire hour just chatting about introductory stuff, the theorems I actually want to talk about are problems that are and are not finite state on deterministic finite tree automata. So this is like finite state machines for graphical input, like knots and manifolds. But I will come back to that. But what you get for free, if you have a finite state problem on a tree automaton, is you get a running time which is not linear, but it's for a fixed parameter, right? If you fix the tree width of your input, which is just some measure of a graph, then for free, your algorithm is linear time. Right? But anyway, so you actually get running time complexities out of these things. Okay, but I want to say a little bit more before I get to that. So we'll come back to tree automata, and that will be the meat of the talk. I do want to talk a little bit about logarithmic space. Right? So somehow this is constant space because you have no memory to store stuff in. Your only memory is just saying what state is my machine in. Yeah? Logarithmic space is where you're allowed to have an arbitrary tape. So now you have a Turing machine. Right? It's a Turing machine, which is like one of these things, where you have an arbitrary tape where you can store stuff and come back and read it again. Right? And this is how you typically model algorithms algorithms that you can write in C code more or less correspond to things that you can run on Turing machines. Right? With some asterisks. But logarithmic space says your scratch space is only allowed to be at most logarithmic in the number of bits of input. So if your input size has n bits, you have a graph with n vertices or not with n crossing, you're only allowed to store a scratch space with log n bits of stuff. And if you think about what this means, what it means is, if I just want to store an index to a crossing, right? So my algorithm starts and says, pick your favorite crossing, that's crossing number 17. Write down the number 17. That number is going to have log n bits, because it's going to be between 0 and n, right? So just storing a single variable of ordinary size, right, polynomial in n, will take log n bits. So effectively, by saying your log space means that you are only allowed to store a constant number of variables. So you can't store sequences. You can't store auxiliary matrices whose size grows with the input. You can't store anything other than a constant number of variables. So this makes problems in log space quite hard. One of the famous ones is called ST connectivity. And the idea with ST connectivity is this. The input is a graph. Right? The input is some graph, along with two vertices, S and T, in the graph. And you have to tell me, are these two vertices connected in the graph? Right? Now, how would you do this if you were actually writing the code yourself? You do a depth first search through the graph. Right? But a depth first search has a stack which grows linear in n. Right? Or you keep sequences, recursively try different sequences of length n. You can't store a sequence in log space. So you have to do something clever. Right? And this was a big open problem for a long time, around, I think it was 2005. My date may be wrong, but the name is not. Reingold. Reingold came up with an algorithm to solve this problem in logarithmic space. And it's not a trivial algorithm. So it does some mad stuff with expanded graphs that one day I hope to understand, right? But it's not trivial. Basically, you grow the graph until the problem becomes easy enough to solve, and that's another story for another time. So this is a hard problem. Just testing connectivity in graphs in log space. One thing that you get for free with log space is a polynomial time algorithm. So if you can do your algorithm in logarithmic space, then for free, your algorithm runs in polynomial time. Because the number of possible states that your machine can be in is bounded by the number of possible choices of bits for your constant number of variables. And that's essentially 2 to the power of log n, which is polynomial in n. Right? So if you are log space, then for free, you are polynomial time. Of course, I mean, it's usually proving it's polynomial time is much easier than proving it's log space, right? Maybe one thing I will mention, if you want to see a log space proof, that is just a cheap trick, but is something in topology. So there's a paper with, joint with Marielda and Arcadius Kalka and Stefan over there, Stefan Tillmann, which proves that two-manifold homeomorphism is in log space. So my input is a pair of triangulations of two manifolds, and I say, are they topologically the same? And you can have boundary, you can have disconnected components, right? And we'll test this in logarithmic space. And when I say it's a cheap trick, what we do is we just reduce it to ST connectivity, and then we use the Reingold machine. Right? So, but there's a topological problem with this in log space. Of course, it's.
Sorry, could you say ST connectivity again? I think I missed it.
Input is a graph and two special vertices, and you have to tell me if they're connected. Yep. In log space, harder than it looks. I gave this to one of our Olympiad students once as like a puzzle over dinner. He came back to me the next day and said that's really hard. Yeah.
Do people actually use this algorithm in the ST?
Well, do people actually use this algorithm? So if you're doing computational complexity, then you use it because you want to reduce things to it so you can show that things are in certain complexity classes. In practice, how do you test whether two vertices are connected? You do a depth first search through the graph, which is linear time. And because your input is already linear size, it already takes linear time just to read the input. Yeah, so you just do a depth first search in practice.
So should we be thinking of this as the space we always work in? Because I only have 8 gigabytes of
Yeah. It's just the space you always work in. I mean, strictly speaking, the space you always work in is finite state automaton, right? Because this machine has, I don't know what gigabytes of memory, so there's 2 to the power of something very large, possible states it can be in, and that's it. I don't have an infinite tape on this phone or your laptop. The reason we don't use this as a model of computing is because you can't even multiply in finite state. You can't test for palindromes, like basic things that we just think are trivial. you can't do in finite state. Once the input gets sufficiently large, which it never will in practice, but Turing machines somehow get around this problem. So the Turing machines you can prove are, the things you can compute with Turing machines are exactly the same as the things you can compute with Gödel's notion of recursive functions, which are exactly the same things you can compute if you could write C code with arbitrary precision integers. And so these things all kind of represent the same class of problems. And there's the Church-Turing thesis, which says that this essentially models any reasonable definition of a computer. But I'm not sure if that's the question. Yeah.
Yeah.
Okay. Okay, so that's what I really want to say about log space, because I want to get to finite state, right? But still, before I get to finite state, we've talked a bit about space complexity. I want to talk about parametrized complexity. So I'm jumping into a different topic here, but I promise you it will all link back, right? So the idea of parametrized complexity. Yeah, let's have an example. All right, so the idea of parametrized complexity is you have a problem, like unknown recognition or connectivity in a graph or whatever it is you like, and the input is your usual input, which has size n. So this is what you would normally talk about when you're talking about computational complexity, and some additional parameter k, right? And this could be some feature of the input. It could be, well, it could be a feature of the input. It could be part of the question. So I could be saying, does this not have genus k? And then my complexity will be measured not just in terms of the size of the knot, but also in k. I could say, what is the genus of my knot? And k is some measure of the complexity of the knot. Right? But the point is you have some extra parameter, and then your running time is measured as a function of n and k. Right? As a function of n and k, and you have this notion of what is called fixed parameter tractable. And fixed parameter tractable means that your running time is some function of k, any horrible function of k, times a polynomial in the input size. Right? So the point is, for example, if you want to measure the genus of the knot, and if k is the genus that you're looking for, so you say, is there a spanning surface of genus k? And suppose my running time is k factorial times n. Then it's a slow problem in general to solve, right? But if I want to say, does this not have genus 2, then the running time becomes n, because my 2 factorial becomes a constant. Right? And the knot can get as large as I like, but this 2 factorial is just a constant. So for a fixed k, it becomes linear time. If I say, does this not have genus 1000, then I have a constant of 1000 factorial, but if I fix that 1000 and let the input grow as large as I like, as long as that 1000 is fixed for once and for all, then it's a linear time algorithm for that particular value of k. So this is why it's called fixed parameter tractable. Tractable meaning polynomial time, fixed, k is fixed.
The polynomial is not a function of k, is that correct?
Sorry?
The polynomial...
Yeah, so k cannot be in here at all. So when I say you quarantine the complexity of the problem, somehow the complexity has to be, like the function of k is all out the front. In particular, the exponent of m cannot involve k. It can't be n to the k, it's got to be legitimately n cubed, n squared, something to that effect. Why is this interesting? Okay, so there are a few reasons why this is interesting. One is that software in topology is fast in practice, right? This is a well-known feature of topological software. If you need to find a geometric structure on a triangulation, or you need to find a triangulation that has a geometric structure of your favorite three-manifold, in theory we don't know how to do this. In practice you just give it to Snappy and it works, right? Very, very quickly. You want to recognize the unknown. The best algorithm we have is exponential time. You feed it to Regina, it works, right? In something that's in practice looks like n to the 5th, n to the 6th. Yeah. So in practice, and this is something we saw in the software demos. There was a consistent theme: is that you can compute things that theory says you should be able to compute. So it would be nice to know why. So you can look at things like average case complexity. One of the problems with average case complexity is it's very difficult to talk about random triangulations of three manifolds, because there's a lovely theorem by Dunfield and Thurston that says almost surely as the size of the triangulation grows large, a random gluing of tetrahedra is not a three manifold. Stuff goes wrong at the vertex links. Right? You could talk about generic complexity, which is where you're allowed to throw away a vanishingly small number of pathological cases and just take the worst case of whatever's left. But again, to say what does it mean to be vanishingly small, you have to say that some probability tends to zero, and again you're dealing with random manifolds. One of the problems with dealing with random manifolds, we don't even know asymptotically how many three-sphere triangulations there are, whether that number is exponential in the number of tetrahedra or super exponential. So if you're talking about random three-sphere triangulations, you don't even know the denominator. So random manifolds are hard to talk about. Fixed parameter tractability gets around that because you're not measuring probability of inputs, you are quantifying how good the input is. K you think of as a measure of how suitable the input is for your particular algorithm. So one of the reasons is it helps you understand why, so I just picked up my coffee, talked a lot, put it down and didn't actually drink it. Anyway, all right, good. So parametrized complexity can give us some sense of why. And we can actually prove things about this that we don't know how to prove for probabilistic models. The second thing is that you can actually use this in software. So if you ask Regina to compute Taravero invariants, which are like these Jones polynomial style invariants for three manifolds as opposed to knots, it has two algorithms which it can offer you. It has the default one, which is some heavily engineered backtracking algorithm, which is exponential time, and it has another one in there which is fixed parameter tractable. So it's using some measure on the graph that is the dual graph of your triangulation, and it's one of these algorithms here, with a constant that in theory is horrible, right? But in practice, this algorithm is actually faster as the triangulations get large. You test it over big databases of triangulations, and the fixed parameter tractable algorithm is faster than the backtracking. So these things are actually giving us software that is useful in practice. The third reason you care about this is in terms of non-parametrized time complexity. And let me just mention something here, which came from Monday. So if some of you saw me on a Tuesday morning looking a little bit broken, it was because there was this paper deadline at 8 AM on Tuesday morning, and maybe I didn't sleep the night before to get the thing finished, but what was in the paper was a fixed parameter tractable algorithm for computing the Humphrey polynomial. Right? The Humphrey polynomial of a knot. And what is the algorithm? So the parameter k is the tree width. I will tell you what this means in a moment. It's the tree width of the graph that you get when you just draw the knot and don't take your pen off the page. Right? And then the running time becomes something like, I mean, there's some extra constants inside the factorials that we should ignore, but it's something like k factorial to the power of 4 times a polynomial in n. So if the tree width of the knot diagram is fixed, then the running time is polynomial in n. I don't promise it's linear or quadratic, I just say it's polynomial. But the reason this is interesting, is because for a planar graph, there's this lovely thing, the Lipton-Tarjan separator theorem on planar graphs tells you that the tree width of a planar graph is order of root n, right? So if you take root n and stuff it into that formula, then what you get is an algorithm for the Humphrey polynomial with a running time of e to the O of root n log root n log n. Right? And this is sub-exponential. And this gives you what I believe is the first sub-exponential algorithm for the Humphrey polynomial. And it comes exactly from building something that is not unconditional on a parameter. It has a parameter built into it with a horrible function, but the parameter is small enough and the horrible function is not quite so horrible that when you stuff in the worst case bounds for the parameter, you get something better than you had before. Right? So this can be used to give you unconditional complexity results. Alright, so what will I do next? I will tell you what I mean by tree width, because we're going to be using that for the rest of the talk, and then we will come back to finite state problems on graphical input. which is what the talk is actually about. So let me tell you about tree width.
Ben, so this thing about the Humphrey polynomial, was this previously known as the Jones polynomial? Am I remembering?
So it was known that it was fixed parameter tractable for the Jones polynomial, but I don't believe it came with a specific function of k. Right? So there's a theorem, there's a thing called Courcell's theorem, which is this wonderful piece of black magic that says if you give me a problem in graph theory and you can express the problem in monadic second order logic, then for free you have an algorithm which is fixed parameter tractable, where the parameter is the tree width and is linear in n times a function of the tree width. But the function of the tree width that you get from Courcell's theorem is really, truly awful. Right? It's terrible. But it's fixed parameter tractable. And so Minkowski has this paper where he shows that the Jones polynomial and the top polynomial are fixed parameter tractable. He doesn't use Courcell's theorem, but I don't think, I should check, I don't think it comes with a specific function of k. Yeah, and then in that paper the Humphrey polynomial is left open. All right. So any other questions before? Okay. So tree width. Let me tell you what the tree width is. So you have a graph G, right? Intuitively, what is the tree width? It's the amount of beer you have to drink down at the varsity before the graph looks like a tree, right? It's the amount. It's how much you have to kind of squint and blur the graph until it looks like a tree. So what's going on here? So here's a graph. Here's a graph, right? What you are going to do is you are going to clump your vertices into what are called bags. So here's a bag. Here, I'll call this one A. Here's a bag B. Here's a bag C. Let's use some different colours. Let's have a bag D like this, and a bag E like this, and a bag F like this. Yeah? So we're capturing all of the vertices and all of the edges in these bags. And the point is, when I say how much do you have to squint, I mean each bag is going to kind of get smooshed together in a single vertex for this thing to look like a tree. So what you do is you take your bags, you hook them together in a tree-like structure. So let's start with bag A, hook that up to bag B, hook that up to bag C, and hook that up to bag F, and then maybe beneath bag B we'll have bag D, and then down here we'll have bag E. And I think I've got them all, right? So you just draw a tree, any tree you like, whose vertices are the bags. Right? And there are some rules that you have to adhere to. So there are some rules. So rule number 1, all vertices belong to some bag. You can't leave out a vertex. Rule number 2, all edges belong to some bag. What do I mean by that? I mean for each edge, there is some bag that contains both of its endpoints. Right? The endpoints can also go off in other bags as well individually, but there is some bag that contains both endpoints. Right? And number 3, for all vertices, the bags that contain that vertex are connected in the tree. So what do I mean by that? Let's pick a vertex. Let's pick vertex, this one here. Right? If we look at the bags that contain this vertex, we've got bag C, bag B, bag D, and that's it. C, B, and D. And these are connected in the tree.
So your tree can be disconnected.
The tree cannot be disconnected. Well, okay, if the tree is disconnected, just draw an edge between the bits to connect them. So the tree should be connected, but that doesn't hurt you.
You're giving a careful definition, so I get to ask you, what tree?
Sorry?
What tree?
What do you mean, what tree?
You got a graph G.
Yep.
T hasn't, no tree has appeared on the board yet.
This is your tree. It's a tree, right? It's a bunch of vertices labeled as the bags, and they're hooked together with edges to form a tree.
How do you find this is a tree?
So how do you find the edges of the tree? However you like. You can build this tree however you like, as long as the vertices are exactly the bags, and it follows these rules. So you could draw a tree, and I could draw a tree, And even though we've got the same bag, they could be different trees. But as long as we both follow the rules, that's okay.
Do you have an implicit rule?
Sorry?
Do you have an implicit rule saying that if you have an edge in a bag, you have the two endpoints in the same one?
Yes, yes. So when I say all edges belong to the bag, I mean belong to some bag. I mean for each edge, the two endpoints belong to some common bag. Yeah.
So only number 3.
Sorry?
Only 3 is the limitation.
Yeah, 3 is the only interesting one. Right. So what rule number 3? Are there more questions about this definition?
Do you have like a limit size of the bag?
A limit on the size of the bag? Watch this space. In a bit. Not yet, but in a bit. Right? But so if you have one of these things, this is called a tree decomposition of the graph. Right? So this thing here is called a tree decomposition of your graph G. So if I give you a tree decomposition of a graph, then it gives you a way to run algorithms on your tree. Yes?
Could you explain tree again?
Yeah, so it's just, so you can put the bags wherever you like.
Yeah.
Your aim is to keep the bags as small as you can. Right? You can have lots of them, but the size of the bags should be small. But we'll come back to that. You can hook them together as a tree, however you like. These edges in the tree do not have to correspond to edges in the graph. These edges in the tree, you can hook them together as much as you like, however you like, as long as you adhere to these rules. So these edges in the tree are really, somehow they have to hook together bags so that each vertex...
What is rule number 3?
Rule number 3 says for any vertex in the original graph, you look at all the bags that contain it, and they should give you a subtree, a connected subtree. Right? So you can't have a vertex which appears in bag E and bag F and nothing else. So if it appears in bag E and it appears in bag F, then it had better appear in bag C, B, and D as well. Yeah? So the intuition that you want here is that the tree is telling you the order in which to process things if you're running an algorithm. So what's the algorithm going to do? You want to run some algorithm to solve some problem on your graph. You start at the leaves of the tree, you hang the tree from a root, you start at the leaves of the tree and work your way to the root. And the idea is that each bag, you process all the stuff that's in the bag. Right? And you've got some vertices in the current bag, and when a vertex disappears from your bags, so you move to the next bag and the vertex is gone, then you aggregate. Right? So you take whatever information you had about that vertex and sum up all the pieces, or somehow aggregate it into a smaller piece of data, and then you never touch that vertex again. And this is where your connectivity rule comes in. Right? So essentially it says as you walk through the tree, whatever processing you want to do with this vertex here, you do it here, here, and here, and once you leave that vertex, you aggregate it and just kind of stuff it into your final answer somehow. And it's okay because you will never see that vertex again. Because of rule number 3.
So it's a strategy for dividing and conquer.
It's a strategy for divide and conquer. And if you know dynamic programming, it's exactly telling you how to do dynamic programming of this graph. Right? So the running time of such an algorithm, basically the number of bags, if you're clever, the number of bags is linear in the size of the graph. So the running time is all about how much processing you do at each bag. Right? And that could be some horrible function, but the point is, the running time is a function of the size of the bag times n. Yeah? So these kinds of algorithms are fixed parameter tractable. So let me now finish the definition of tree width. Right, so the width of a tree decomposition is the maximum bag size minus 1. Right? You say minus 1 because it would be nice for an actual tree to have a width of 1. Right? It's like normalizing a constant somehow. And for a tree, if it's an actual tree, you still need 2 things in each bag because you've got to capture the edges by rule number 2. So the width of the tree decomposition is the maximum bag size minus 1. And the tree width of the graph is the minimum width over all tree decompositions. So it's a minimax problem. Right? For each tree decomposition, you look at the maximum bag size and you minimize that by choosing the best tree decomposition you can. And that's the tree width of your graph. And then these algorithms have a running time which is exactly some function of the tree width, which is some function on the bag size, times n, which is is fixed parameter tractable.
But you first got to find your decomposition.
Sorry?
You first got to
You first got to find your decomposition. Yes, so that's an NP-hard problem. So computing the tree width is NP-hard. But by a theorem of Bodlander, it's also fixed parameter tractable in the tree width. So if your tree width is small, then you can find a small tree width decomposition in linear time. Yeah, so it's okay. I mean, it's a hard problem, but if you just want to be fixed parameter tractable, that doesn't stop you.
So if there's a good answer, you can find it, but if there's no good answer, then give up?
Yes, yeah. And so actually, for instance, for Honkling, I mean, that has to be factored in to this running time here, because you get a knot, you don't have a tree decomposition of the knot. So there's a nice approximation algorithm there's a wonderful book on parametrized complexity with 6 authors, I think, and the first one is Seagun, and I don't remember the rest, but they have an algorithm they give in that book, which is an approximation algorithm. It doesn't promise the best tree width triangulation, the best width decomposition, but it promises to get it right within a constant factor, within a factor of 4 and a bit. And the running time is polynomial in the tree width. So you use their algorithm to get a reasonably small tree width, and then this root n actually becomes a 4 root n, and then you stick it into here and it works.
Wait, so finding true width on the nose is NP-hard, but getting a good approximation is not?
Yes, yeah. Like many NP-hard problems, yeah.
So it's not NP-hard on paragraphs. It's not now.
It's not now. Okay. Cool. All right. So more questions about tree width. Okay. Excellent. I think I've actually gone vastly off script, but that's all right. Let me just resync here. All right. Let me come back and talk about space complexity. So just the point is that tree width is a parameter that you see again and again and again in parametrized complexity. One of the reasons is because of Courcell's theorem. If you can express a problem in monadic second-order logic on graphs, then it's fixed parameter tractable in the tree width. In joint work with Rod Downey, we have a paper which does this for triangulated manifolds of fixed dimension. So you have a topological problem which you can express in monadic second-order logic, which is fairly hard for topological problems. But for instance, you can talk about the genus of a surface in monadic second-order logic. Then it's fixed parameter tractable in the tree width. So what this means is you have a whole pile of problems which are just spitting out tree width-based algorithms. To Vero, you can express in monadic second-order logic. It's a sum over states where being a valid state is a monadic second-order logic property. And that's somehow the first time we had a parametrized result on Vero was using exactly that machinery. When I say that Alex Eastwood is coding up solutions to arbitrary problems, they are coding up exactly this machinery, right? So you give the problem in monadic second-order logic, it constructs what is essentially a finite state tree-based automaton to solve that problem. So here we're coming back to the space complexity. I give you a problem in monadic second-order logic, you build a finite state tree automaton, which works over a tree decomposition of your input, and then the running time is linear in the size of the input. But somehow the complexity comes from the tree decomposition. So here we're coming back to the link between running time and space complexity. Okay, so let me go back to space complexity. People who are good at this manage to use the boards in order. Let's go for the middle. It's like taking a cake and just cutting out a little circle in the middle, right? So anyway, okay, let's.
I assume you're using divide and conquer.
Dynamic programming, yes. Yeah. Sorry? Oh, with the boards. Okay, yes. It's a joke. Yes. Because you never joke, right? Okay. So, what do I mean by a tree automaton? Okay. So, what do I mean by a tree automaton? So, if you come back to finite state automata, which I have conveniently just rubbed off the board, but if you think of finite state automata, so like grep, you feed it a text file, one letter at a time. The silly example we have with modular arithmetic, you feed it bits one at a time. It assumes that your input has a natural linear order. Right? And this is reasonable for text files. It's reasonable for bits of integers. But if I said, look for the word Lackenby in this text file, but you're going to process the letters in random order, right? Then it doesn't become finite state, because somehow you have to remember where the L was, so that when you eventually get back to the next letter, you can remember that you're looking for an A, and so on. So suddenly it's not finite state anymore. So the fact that the grep is finite state relies on the fact that the input is coming in a sensible order from start to finish. Now graphical inputs, when I say graphical inputs, I'm thinking knots, manifolds, graphs, don't necessarily come with a sensible linear order in which to put things in. And if you try and force a linear order on them, then you're working with other parameters of the input, such as cut width and path width and so on. But naturally, there's not a sensible order to put on things. But what you want to preserve is closeness. Right? So somehow, I mean, because the reason grep works is because when you read the L in Lackenby, the A is going to come straight after. So you don't have to stash it away. You can just check for it on the fly. Right? So in a similar sense, when we're processing knots and manifolds, we want to process nearby things nearby in time. Things that are nearby in space should be processed nearby in time. So this, in a sense, is being captured exactly by a tree decomposition. Because what is this tree structure giving us? It's telling us things that are somehow close together. And having large bags says, well, they weren't that close together because we had to stuff a whole lot of things into the same place. But if your bags are reasonably small, then somehow this gives you exactly an order to process a graph so that close things get done one after another. Yeah? So we want to use trees as a way of modeling a graphical finite state automata. So here we go. So this is a, what's the acronym? Deterministic finite tree automata. Deterministic finite tree automata. And so everything from here is joint with Mike Fellows. Okay, so the idea is the following. So with a finite state machine, so just a plain old deterministic finite automaton, so the ones that we did at the beginning of the lecture, you've got a bunch of states, right, and you've got arrows that move back and forth between the states, and your machine jumps around from one state to another. But what you can think of is that these states are actually evaluations. So you have your input file, theorem, space, open bracket, Lackenby, close bracket, and so on. Right? So this is your input sequence. Instead of thinking of a machine where you feed it a letter one at a time and it jumps around one step at a time, a different way of thinking about it is that this machine gives you a way to evaluate every position in the input. It evaluates every position in the input. If this is state A, and this is state B, and this is state C, and so on, then the evaluation of this state is A, because that's where the machine starts. Maybe it would have jumped to here next, so the evaluation of this state is B. And the evaluation of, and so on. And you can give a number to every piece of input, every letter of the input, that tells you what state the machine would be in. So this is a way of evaluating every position of your input. And the point is that the formula for evaluating each position of your input says just look at the previous position and the current letter. And there's a function, it's just a big lookup table, that says if your previous position is a C and the current letter is an X, then the next position is an F. Yeah? Just a fixed finite size lookup table. So this is a way of evaluating positions of the input. So a tree automata is going to be a similar idea, but instead of writing your input from left to right, your input becomes a tree decomposition, and you are evaluating bags of your tree decomposition. So you're evaluating nodes of the tree, essentially. Right, so the idea is a tree automaton, the input to a deterministic finite tree automaton is a tree with a root, right? So there's some tree. And you're allowed to put symbols on each node. Symbols at each node, right? So maybe, I mean, these symbols are like the letters of your input here. But instead of being written from left to right, they appear in a tree structure. So maybe the symbols are, I don't know, L, A, C, K, E, N, B, Y, right? Whatever. Yeah? So you put a symbol on each node, And then, exactly like before, you evaluate each node in order from the leaves up to the root. And so you have some rules.
So before you started with the capital T, would that have been the root or a leaf?
The T would have been a leaf, right? So your rules say if you're a leaf, then it's just some function of the symbol at the leaf that tells you how to evaluate the leaf. If you're not at a leaf, it's a function of the symbol at that node and the evaluation of your children. Right? So there's a rule that says if the current letter is a C, and this child evaluates as 67, and this child evaluates as 93, then lookup table says this node evaluates as 74. So just like here, except here the evaluation says look at the current symbol and the previous evaluation. Here it says look at the current symbol and the child evaluations. So instead of working left to right through the input, it works from the bottom to the top of the tree. Right? And somehow, I mean, if you want to think of something happening in real time, you think of the different branches happening in parallel. And then eventually they merge at parent nodes and all the way up to the root. Right? So what's a good example of this?
So
a good example.
You say okay, so you take this C and it's got certain children. Is your output a new value of C, like a new state?
Your output is going to be a state of the machine. So the evaluation is a state of the machine. Yeah.
Is
So
the state structured like this tree or a single?
no, the state is just any old. I mean, this thing here you draw states as circles and arrows, but what the states really are is they're just names, A, B, C, D, E, and rules that say if you're in state A and you see an X, then you move to state B. So the states are just, they don't have to match the letters on the nodes. The states can be, let me give you an example. I'll give you an example.
The nodes are
But if the C, you do something and C has its children and you get something new, you get into a new state then. But you get into a new state that's no longer lacking in it.
No, those aren't states, that's the input.
Let me give an example. I'll give an example. This can make exciting noises. Okay, so an example is parsing arithmetic expressions. Right? So your tree is going to be an arithmetic expression, right? So for instance, suppose I'm giving you 1 plus 0 times 1 plus 1 plus 0. So this is arithmetic in Z2. Right? So as a tree, let's put brackets around everything. As a tree, what does it look like? We're adding 0 and something, and what's in the middle here, it's the addition of 1 and something. What's here, it's the addition of 0 times 1 and 1. Right? So here's an arithmetic expression that I've drawn as a tree. The symbols on the nodes, which are part of the input, are 1, 0, plus, minus. The states of this machine, the states are just going to be, because I'm evaluating in Z2, the states are just going to be 1 and 0 is our output. And the rules are, if you're at a leaf and the symbol is 0, then the evaluation is 0. If the symbol is 1, then the evaluation is 1. If you're at a plus symbol and the child evaluates to 1 and 1, then you evaluate to 0, and so on. So the states don't have to match the symbols on the tree. Yeah? And in this case, the state would be the result of the formula, and the symbols would be the input for the formula. Does that help?
No. Is the state the thing you get at the top of the tree?
Okay, let's do this. So the states are 0 and 1. And so the rules are, if you have a leaf which evaluates, well, if you have a leaf with the symbol of 0, then it evaluates to 0. If you have a leaf with the symbol of 1, then it evaluates to 1. If you have a child that evaluates to 0 and 0 with a plus, then it evaluates to 0.
I think to answer Caroline's question, maybe the state of the root is the answer.
Oh, right, sorry, yes. Yes, so the answer is the state of the root of the tree.
Right, so you run through this whole thing bottom
Bottom
up
to
and
top.
you come up with something at the top and that's your state.
Yep.
Okay.
And so just like in the original example, the state, with that mod 3 example, the state that you end in tells you whether your answer was yes, because you have to be in this state if the answer was 0 mod 3. In the same way, the state at the root of the tree tells you the final solution to your problem.
Okay.
Yeah, sorry, yeah. More questions? Okay, so what does it mean to be finite state on a tree automaton? It means that if your input can be written like a tree, then there is some finite state machine that runs through the tree and solves your problem. Like a finite state machine at the beginning of the lecture gives you a linear time algorithm for free. If you have a finite state tree automaton, then it gives you a fixed parameter tractable algorithm for free. Because you build the tree, and then like grep, you just feed the input through the tree. And the running time is order of n, right? The size of the tree. However, knots and manifolds are not trees, right? So let me show you how to turn your favorite knot or manifold into a tree. Right? So turning graphical input, well, turning a graph into a tree. So here's the trick. Here's the trick. Suppose your graph has tree width t minus 1. Suppose your graph has tree width t minus 1. Then it is possible to build your graph using the following instructions. So at every stage, you're going to inductively build your graph just from the ground up, right? Just starting with a few vertices and hooking on edges and nodes and merging pieces together and eventually building up your entire graph. Right? And the way you do it is at each stage, you have what is called a t-boundaried graph. What is a t-boundaried graph? It is a graph with some special vertices labeled 1 to t, some special vertices labeled 1 to t, and a whole bunch of other vertices which are anonymous, which are unlabeled. So a t-boundaried graph is just a graph where you label t of your vertices specifically with the labels 1 to t, and everything else is just unlabeled, anonymous. So the way you build your graph is using the following instructions. Alright, you've got the instruction 5, which just says build an empty graph.
So t-boundaried graph?
Sorry, t-boundaried.
T-boundary graph.
T-boundaried, it's my handwriting.
So everything is labeled? No.
No, so there's t vertices which are labeled with the numbers 1 to t,
Everything else.
and everything else is anonymous.
Okay.
So 5 says build an empty graph with vertices 1 to t. So this is like your starting step. You just plonk t vertices down, label them 1 to t, and there's nothing interesting. You have an operation called sigma, which cycles your labels. Right? So 1 becomes 2, 2 becomes 3, 3 becomes 4, t becomes 1. Yeah? You have an operation I, which says swap labels 1 and 2. So with these two operations, you can commute the labels however you like. Right? You have another operation, which is E, which says join 1 and 2. So this inserts an edge. This inserts an edge exactly between vertices 1 and 2. So if you want to put a new edge in your graph, you use these operations to rearrange the labels so that 1 and 2 are sitting on exactly the vertices that you want to join, and then you use this operation to join. Right? And there is U, which says you make a new vertex called 1. So that adds a new vertex to the graph, labels it 1. The old vertex, which was called 1, loses its label. It becomes anonymous. Once something loses its label, you can't touch it again. Right? That's the point of these t-boundary graphs. There's only ever t vertices where you're constructing things. And like in a tree decomposition, once you let go of a vertex, once it loses its label, it's gone. And you can't touch it again. And then there's the final operation, which is the interesting one, which is plus. And plus says merge labels. Merge labels. So the idea is you have a graph G and a graph H, and what do? You take the vertex 1 from G and 1 from H and make them the same. So it's like a union of two graphs, but you identify the vertices with the same labels.
And you get multiple edges, possibly.
You can have, or you just make them the same. So if you've got parallel edges, you just merge them into one edge. Yeah? So how do I present a graph as a tree? I give you instructions for how to build it. 5, sigma, E, here's something else. Take these two graphs, merge them, keep going. Right? So I give you instructions on how to build a graph, and these instructions can be hooked together in a tree, just like an arithmetic expression. And in particular, if you have a tree decomposition of size at most t minus 1, or width at most t minus 1, then you can do this with t-boundary graphs. And then what are the labels on the vertices? The labels on the vertices are somehow telling you the instructions for building the tree. And then your algorithm walks through the tree, follows these instructions for building the tree, and solves the problem. So that's how you give a graph as graphical input. If you want to give a knot as graphical input, you basically do the same thing with adornments on the vertices, because the vertices become crossings, and you say whether it's over or under. Right?
How long does this algorithm?
Sorry?
How long does this pre-processing take?
The pre-processing, it's fixed parameter tractable in the tree width. So if the graph has small tree width, then all of this pre-processing takes linear time in the size of the graph times some function of
Tree
tree.
width means what?
The worst bag size.
Oh yeah.
Yep. So basically, if you can bound the sizes of the bags, then this is all linear time. So, so what's the point, right? So, and if you have a manifold, how do you give it as a tree? The vertices of the graph are tetrahedral, so you adorn the vertices with information on which permutations you're using to do the gluings to adjacent tetrahedra. So this is how you feed your topological data as graphical input to a tree automaton. So the theorems, let me write up in the last 30 seconds some actual theorem statements. Okay, so we have some theorems about things that are finite state and things that aren't finite state. So yes to being deterministic finite tree automaton. Well, let me start with no first. You cannot recognize the unknot in finite state. This is probably not surprising. You cannot recognize the free sphere. You cannot recognize S2 cross S1. You cannot recognize whether the first homology is trivial. You cannot recognize whether the fundamental group is trivial. You cannot recognize whether the first homology is finite. You cannot, there's some other cannots. There's a whole bunch of things here which look like different theorems, but they're all the same construction, which is in the same way that you show that palindromes can't be recognized on a finite state machine, you show that working out the exact layered length space that I give you can't be recognized in a finite deterministic pure automata. So it's just the same construction with layered length spaces, except for unknot recognition. That's a slightly different construction. Things that are finite state on a tree
So
automata.
is that not the pump? The only thing I remember from my finite state class is the way you prove that something is not detectable by a finite state machine is by a pumping lemma.
Yeah, so there's a few ways, which are all essentially doing the same thing in different ways. So there's the pumping lemma.
It's morally that sort of.
It's morally that sort of
I
thing.
mean, can you illustrate the pumping step in any of these geometric?
So that's up to the chair because I'm 2 minutes over time already. Okay, maybe 30 seconds when I finish, if the chair lets me, I'll show you. But yeah, you've got the pumping lemma, you've got mile on a road, which is a different aspect on the pumping lemma. You've got test sets, which are a different aspect on the pumping lemma. And any of these can be used to prove this theorem. But essentially, like palindromes, for unknot recognition, the trick is, so I'm answering the question now without asking the chair, but the trick is to build a knot, is to build a knot that does this and then untwists
Like
in the other
lots of
direction.
times, like more and more times. This is the unbounded thing
Yep.
of the pumping.
Yeah. And basically, you have to. The number of twists has to be the same as the number of untwists, or otherwise you don't get the unknot. That's the trick.
Parentheses match.
Right. Yeah. So things that are finite state, recognizing your favorite two manifold. Right. So two manifold homeomorphism is log space. Recognizing whether the two manifold is specifically the sphere is finite state. Specifically the torus is finite state. Specifically your favorite manifold for your fixed favorite manifold is finite state. The Arf invariant of a knot is finite state. So this is actual three-dimensional invariant. It's a simple three-dimensional invariant, but it's a three-dimensional invariant, which is finite state. Essentially what happens here is that it's evaluating the Jones polynomial at I, which means all of your exponents can be reduced to modulo 4, all of your coefficients can be reduced to modulo 2, so you compute the Jones polynomial, but only ever remember a fixed amount of stuff. That's the idea. I will stop because I'm now 4 minutes over time, but I have a theorem statement for you, so maybe that's a good place to finish. This gets cold after an hour. Yeah?
So while Ben finally gets to enjoy his coffee, does anyone have any questions?
So, I guess I'm interested in how your algorithm for the Humphrey compares to just doing the naive thing and scanning in a skinny direction. So does it improve over that?
Scanning in the...
So if I have a knot diagram, I can just try to find the skinny direction.
Right, finding a skinny direction. So
scan that way.
yeah, so there's a skinny direction which is order of root n. I'm not sure. Do you know how fast it is to find a skinny direction? I'm looking at Arno because Arno has
From a diagram, yeah.
That's computing the path widths.
I think you want not the path width because you actually want it to be with respect to the planar embedding. So I think you want like somehow you're taking cross sections, but cross sections have to be planar cross sections. So you have like a sweep across the plane. I think this is what you're describing, right? A sweep across the plane, and you want to minimax the number of edges that you cross.
There's some calculation you have to do, or you see a cap.
Yeah, I mean certainly if you can do that, then you can build something which is FBT in the number of edges that you cross the most during the scan. And so the things you have to do is A, get the details of that, and B, find a way that is fast enough to find a root n size scan, which I think is an NP-hard problem, but almost certainly fixed parameter tractable, right? And must be fixed parameter tractable. Maybe it's not NP-hard on planar graphs, I don't know. But you have to bound that and then somehow smush all the things together and get something. Yeah, so I mean, my gut says you should be able to do it, and I invite you to do it. Yeah. Sorry, yes.
Well, some of the things, but it feels to me like this might describe some sort of biological process, because you're talking about looking at sort of very close finite range interactions, a bunch of things that trigger other things just very locally, but you're describing a process whereby this very big complicated array can kind of go through itself without interfering with other things after a while and moving into some new condition.
Okay.
So that was one thing. The other, if you were trying to do some horrendous sort of modeling of some very complicated physical system, again, you're trying to do it, say, by finite elements, but this is saying, well, you sort of do it in all these patches, but actually you have a way of scanning all the patches without having to worry, you process them in some sensible order that you can kind of get. Anyway, it just seems like it goes much further, potentially, than just, the kind of topological problems that you're talking about. I don't think anybody has tried doing that.
Yes, I don't know either. This is kind of unrelated to your question, but your question, which is a complicated question, but it's unrelated. But the people who do parametrized complexity, it somehow grew up in graph theory and logic, but there's a sizable community of people using it in biological applications. But the biological applications there are more like evolutionary trees and things. Phylogenetic trees, is that the word? Have I got the right? Phylogenetic trees, yeah, trying to merge together sort of different things that come from different measures of closeness of DNA. I think so that crowd gets excited about applications which are outside native graph theory.
Any more questions? Let's thank Dan for his wonderful